Maybe let's just get started. So hello everyone, I'm Junkun Chen from UI CCS department, and today I present Tryon 2.0 long-form high-resolution fully immersive videos, which will actually include 2 consecutive research projects in my virtual Tryon video generation. So today the official topic is the virtual fitting room, but today I will cover its previous objects and dance because these two are highly connected with each other. So let's get started. Let's consider a very common scenario in the real world. A customer enters a clothing store where a piece of clothes caught their eyes. Therefore, they take this clothes into a fitting room, try it on, and show different poses in front of a mirror to see how it works, or perform some different motions to see its dynamics like this. When shopping for clothes online, customers expect a similar experience to in-store try-ons. They also want to see how they will look like in the garment and also preview it in various poses and motions as if they are on site. These expectations make video-based immersive virtual try-on essential. The customer uploads their image and the garment image, then select a reference video to define the desired motion. They want to preview how the outfit looks on them realistically and dynamically. However, this kind of virtual try-on remains highly challenging even for images. State-of-the-art open-source models struggle to accurately render the garment, while only commercial systems like Clean succeeded. However, simply animating an image-based results fail to preserve occluded garment details as shown in this part. So the detail is like there are 3 white points, but in try-on results, it will become some scattered points. In this presentation, we highlight our high-quality video try-on results that bridges the gap between the between the virtual and on-site try-on. So we not only achieve high-quality, high FPS try-on on fixed 5-second videos, but also overcome the constraint of time and generate long videos and arbitrary depths. So these are achieved by our end-to-end virtual try-on video system, stress and dance and virtual fitting. So notably, we are the first to enable virtual try-on in videos at high resolution and high frame rate, and also the first to generate minute-long video try-on videos. So our results surpass SOTA image-based methods and achieving SOTA in both image and video try-on. Achieving this high-quality end-to-end try-on involves some key challenges. First, it must handle heterogeneous multimodal inputs, text, images, and videos, while distinguishing their unique roles, such as garment photos versus user images. Such complex conditioning is not addressed by previous work. Second, training a video generation model end-to-end demands a larger amount of video data. Compared to abundant image datasets, video, especially long-form video, is significantly scarcer. Third, generating long videos often lead to degradation, including morphing artifacts and temporal inconsistency. Our goal is to prevent both in the output. To address these challenges, we introduce 3 core designs. First, we propose ContNet, a general framework that unifies heterogeneous input into a single homogeneous token sequence, which is compatible with any transformer-based model. This enables the generator to consider all of these conditions jointly while respecting their distinct roles. Also, to leverage abundant image data, we propose a hybrid training strategy that includes both data efficiency. We also introduce a triple generation mechanism to augment the data. And finally, for long video generation in VFR, we develop an autoregressive framework that reduces the compute cost and removes the need for long video training data. This method further enforces global temporal consistency, ensures smooth and coherent appearances. Now let's begin with the conditioning. In a typical diffusion model, we take the noisy video and text prompt as the input, encode them into token sequences, and feed them into a diffusion transformer or DIT blocks. Within each block, the 2 sequences are concatenated together for self-attention, then split again before passing to the next block. Finally, this video token sequences is decoded into the output video. In this straightforward design, we observe the self-attention learns the correspondence between video and prompt, allowing them to fulfill the instruction. Building on this insight, we extend to more conditions by converting each by converting each of them into a homogeneous token sequence via appropriate encoders. We then expand the DRT to attend to these conditions when generating the video, so that we just project each sequence into the feature space of each DRT layer, reusing the fit-for networks and mirroring the DRT architecture. This forms our condinet. To improve efficiency, we further apply LoRa with shared parameters, allowing distinct behavior between different conditions. So in this case, we just simply concatenate all of them within the inputs of attention and obtain the output. Through this reasoning, we can generate high-quality videos that faithfully preserve all of these conditions appearances. Only that solves the challenges in the model architecture. Now we will move to another topic of training data. Training data for this try-on task presents two major challenges. First, most internet available data is paired, containing a garment image and the video of the user wearing itself. However, for training, we actually require these unpaired triplets, including an extra image of the same person in different outfits. Data is hard to collect online as there will be few persons capturing appearances in different garments. On the other hand, compared to the abundant paired image datasets, video data is significantly scarcer, especially the long-formed ones. This causes a training framework that is highly data efficient and can fully exploit the limited video resources we have. Therefore, to generate this missing user image impaired data to make it triplet data, we introduce a straightforward triplet synthesis pipeline using existing image-based virtual try-on methods. We just sample a frame from a video, select another garment from our dataset, and apply an existing try-on model to synthesize this missing user image. And also, we can use it as the true input and target for try-on, removing the needs for some workarounds like agnostic mask lens poses. Even if the generated image has artifacts, it still remains effective because it is the input instead of the training target. We propose a hybrid training strategy to incorporate image data into a video generative model. Each training batch includes one video and several images, like this. The image helps the model lens accurately try on from abundant image data, while the video maintains its capability. This approach is both data and compute efficient. During early training, we use low resolution video and full resolution images, allowing faster training and convergence while at minimal cost preserving both of the high resolution capability and the 5-second capability of the pre-trained diffusion model. And then we can move to the full resolution to make it still reach the desired quality. So with this training strategy and our architecture, we can achieve high resolution high resolution try-on as short videos in dress and dance. Now we will move on to the long video try-on here. First, how should we scale up in dance in virtual try-on videos? Similarly, there are two key factors, the architecture and the data. In the dress and dance, we generate a 5-second long video by denoising this kind of clip. A naive way to extend the length is to just scale the 1 minute long video directly, but it has also major drawbacks. First, its length is fixed. Second, it is time and memory consuming because it grows quadratically. Third, it requires the real long video data, which is just less than 1% in our dataset. Therefore, inspired by large language models that does some autoregressive generation, we also propose this kind of autoregressive fashion diffusion model generation. We are going to generate the frame segment by segment and finally compose them into a long video. This method, first, it can be flexible for arbitrary lengths, and it can be theoretically infinite long because we can always append a segment. Second, it enables efficient training because the generation time just grows linearly with the length of the video. Third, it only leads short 5-second long video data because at each of our time, we just consider a short clip. So we don't need any of the actual long video data. However, this kind of generation also introduces two key challenges. The first is local smoothness between two overlapped segments. So including some sudden changes or morphing as shown here, you can see it's just become shorter suddenly. And a second is the long-term or the global temporal consistency happening in two segments that cannot see each other. This is presented as some inconsistent garment appearances, like this, the length of the dress is different, or some inconsistent back or side views. So to ensure this consistency, one idea is to first have this 3D mesh of the person wearing the garment, so that each frame can be rendered from the mesh after deformation and also keep consistent with each other. However, this kind of 3D generation is even more challenging than the video. So instead, we converted it to an equivalent video, which is a 360-degree view video, which can be theoretically converted into the 3D scene, or it can be regarded as a 3D rendered version of this 3D mesh. Since the video can have this 3D explicit 3D correlations, it effectively contains the same information, which is the full body appearances of the user. We then use it as an anchor to enforce consistency across frames. So in this case, the framework just like follows. First, we generate this anchor video, and then we use this anchor video to guide each of the generation so that it will keep consistent with the anchor video, and each segment will be consistent with each other. Now we have finished this methodology part, so now I will show some results. So first, dress and dance can support multiple modes through the content design, including single garment, multiple garments, and transferred garment. And it can generate high quality, high fidelity results that preserve both garment and user appearance as well. And it outperforms the clean in not only fidelity of the user and garment, but also the try-on capability. And this also happens in our multi-garment try-on mode. And also the segmented or transferred garment as shown here. Notably, our resolution is at least twice as the baseline. Our dress index is also even able to perform text ID trial by simply changing the text from descriptions. Due to the time constraint, I will quickly go through the results here. And so because these VFR results are long videos, which are time consuming to show, I will just quickly go through them. And if you are interested, you can check them on our project page. And so as the takeaways, in the dress and dance, we unified the multimodal conditions using coordinates and use the hybrid training strategy for data training. And in VFR, we have the auto-regressive generation and also proposed the anchor diffusion model to ensure the consistency. Thank you for listening, and please feel free to scan these QRs because I know this will be recorded and posted on YouTube. So I just want to stay here to bring the convenience for the watchers. Thank you. And any questions?
Thank you for your presentation. It was very impressive for me to use anchor video for constant long video generation. I have some question that during diffusion process, I saw that you concat all the features and do attention, but I did it a similar way to concat different modality, but for me it was very hard for me to attend a different modality. So is there any problem, or is there any the solution to divide or attention more on the another modal condition?
This is actually a very good question. It actually is related to something that I'm not showing in this project, in this presentation, but actually it is emphasized in the original paper. So this is actually about the attention dominance problem or the attention sink problem. that is more usual in large language models. So in these problems, for example, in the diffusion model, the model may just look at the original text or image modalities instead of some new modalities or newly introduced modalities. That's because as the model already have some capabilities from those modalities, and they are too lazy to learn their parameters towards those new modalities. So my idea is just to construct some curriculum learning stages so that we can strictly guide the model to focus on these new ones. So my strategy is like this. So in this project, the actual issue is that when I introduce this garment condition, it is actually very hard for the model to learn that I have to look at this garment. But sometimes they just look at this text prompts because they're in the text prompt, there will be a description of the garment. So the model just ignore this garment. So I conduct several stages. For example, the first stage is that the video, instead of a human video, is actually a fixed video having the garment in the middle for all the frames. So it is just like this static frame times, for example, 5 seconds. So this will make it very easy for the model to learn from the garment image because the model just needs to learn to copy from this garment image and then it just makes the loss very small. So this is actually a very good guidance to encourage or guide the model to get out the attention dominance on the text and to look at new modalities. And then after the model achieves this, we can finally go back to our original task because the model is already looking at these garments. And this looking at is actually modeled by this attention layer. So as the attention is already, as the model is already paying attention to these parts, then we can move to the floor task so that the model will be able to use them. So I think generally, if you have some other modalities, even like audios or like 3D things, you can also construct some intermediate stages so that the model is easier to learn. For example, I'm actually also doing some projects in 3D video conversions and generations, which is like which is like the one paper I just presented today. But it is different that the model needs to directly take the 3D mesh as the condition into the diffusion model. So this is actually very hard for the model to directly consider, and I did fail for several months. But finally, the working idea is still the similar, that I construct a specific video so that the 3D can be directly constructed into that video, and the model will be very easy to learn this modality. And I believe that something like audio can also somehow happen here because I know that you are doing some projects related to audios. So I think if I were you doing this project starting from some pre-trained models, I may also try this kind of way. For example, to construct some special videos that just showing the changes of the audio, so that the model will start looking at the audios, and then after the model can achieve good loss here, I can finally move to the ordinary training to guide this simulation. Thank you.
Yeah. Yeah, thank you for your question. And thank you for sharing your experience. Yeah, thank you.
I also have some question, or if you have further questions, please go ahead.
If there are questions, just feel free to ask anything.
Okay, so I got a question about the data. So I had a very similar question as Jibin because I was wondering about how to balance the modalities here. But I guess the other important part of this is the data, the paired data. You also spend quite a bit of kind of resources on explaining how the data pairing was or tripleting was done.
Triplet generation.
Yeah. So I wonder, can you remind me where you got all this data first place?
So,
I think I missed that part.
So this is our data set, overview. So we have some image data and some video data. these data are just crawled from the internet. Like for example, some websites will have some previews of garments and users. For example,
Mm.
just most usual like Nike or Adidas, like those companies, and also Ralph Lauren's, they have some websites, and the websites will have a model wearing the garment and also have the flat garment, and some of them also have the video. So we just
Mm.
brought those data set for this research purpose. And we actually also have some captured data set that we hire some crowdsourced workers and sign some contract with them to capture those
Mm.
data. But that is kind of not very usual. But for this kind of data, the cross data from the internet is more usual in this kind of research. So this is just the scale of the data that we can have. As clearly shown here, it is actually very long tail with
Mm.
correspond with respect to its video depth.
Mhm. Do you roughly know whether each of the data sources contributed eventually? So, for example, the long video data, I guess this is your self-collected data source, right? And presumably have higher
No,
quality, no?
no. So this video data is still the crawl data. So some of the
Ah,
websites
okay.
have some like 30 seconds of data, and in our capture, we can definitely make it long. But for the internet ones, we still want to have them because the self-capture data is actually with very very low diversity, especially in the like the models and the backgrounds.
Mhm, mhm. In any case, my main point is I'm wondering if every data source that you considered eventually actually contributed to training the model to kind of perform well.
So at least the model will see each of the data at least once, because our training takes
Mm.
long. It can see all data. But I'm not sure whether, for example, whether each website or each single video will have the final contribution, but I believe that it will contribute the model's diversity. And also
Mhm.
in this kind of chip generation, it not only requires a this video, but also requires another garment. So collecting this single garment inputs will also help the diversity of these synthetic triplets. And I believe this is another source of the contribution from the data to the model capability.
Mhm. Yeah, that actually answers my question. Super cool work.
Thank you. So any other questions? And if not, maybe we can move to the next presentation.
I have another question. Um, in your method, you use motion source video.
Yeah.
So extracting pure motion while removing the identity information, it seems quite hard. So did you manage to isolate motion without leaking the identity into the generated video?
So actually here we just use some intermediates. Here we are using a model called the VIT pose that we convert the input video into this like just skeletons and key points. And so in this case, we can just remove the identity. And ideally, I can train a model that it can directly support real world video here. But this will make it even harder to train. And this VIT pose also brings some convenience because first, you don't need to make this host person to be the same as the actual person because it just effectively remove everything, not only the identity, but also like how tall or short and fat and thing like this. So in certain situations, for example, here, the motion source can just be a different person, or even like just even, for example, here, the motion source is rotating statically. So in this case, I think the model will be able to do well with this reality process. And another core reason is that this VIT pose is sparse, so that this sequence can also be sparse because we only care about the foreground or the colored part of these skeletons. We don't care about the background. So we can just keep the tokens that at least include some non-empty pixels and only put these bars here so that this will be very efficient. It will just be so the final number of tokens will just be comparable with images instead of this very long video. Does this address the concerns?
Thank you for answering. I forgot to catch the skeleton. Thank you.
Yeah, I didn't. I did not measure the skeleton. The idea is just that we have this right because time is limited and I cannot cover every details. But if you are interested, you can just check the paper or ask me through Slack. I believe Slack will be able to handle some more Q&As. Thank you. Maybe we can go to the next.
Oh, sorry.
So the next presenter will be Jibin Song, and they will present a paper called Syncphony Synchronized Audio to Video Generation with Diffusion Transformers. So this is the this is the audio modality that is different from my modalities like images and videos. So let's welcome Jibin to their presentation.
Thank you for introducing me. Yeah, I'm a graduate student in Yonsei University and advised by Young. As you introduced me like that, I'm interested in video generation, such as fast sampling and audio to video generation. Today I'm going to talk about Syncphony, synchronized audio to video generation with diffusion transformers. First, what is the audio to video generation? Audio to video generation is to generate videos that synchronize to audios. So in this task, we control the motion, how many times and when the dog barks exactly align with the audios, and when the ball is released and how quickly it travels and when it hits the pins. The video below shows the conditioned on-shifted audio with the same image input. So even though it input condition on the same image input, it can control the motion using the audio conditions. Oh, sorry. But existing audio to video generation work have some problem. They are struggle with fine-grained synchronization between audio and motion. That's because the indirect mappings, they fail to reflect the complex and detailed temporal structure in audio signals. Such as magnitude-based adjustment and audio-to-text projection. So magnitude-based adjustment is to multiply audio magnitude to attention score, which doesn't align with real-world scenario. As shown in the video, like that. Audio has a continuous rolling sound, but motion is keep changing across the temporal axis. And another research was to project audio into text space. This could ignore the audio's temporal structure because text is simple to interpret the audio's temporal structure. So to solve this synchronization problem, we apply this framework. we apply cross attention with rope to enable direct audio-video mapping. We experienced without rope, but we could not capture the temporal synchronization, so rope is essential for alignment. And we build on pre-trained video backbone to utilize the ability of generating high video quality. But training this architecture with the standard diffusion laws alone does not yield good audio motion synchronization. So we propose two core methods to improve synchronization. First is training time. In training time, we propose motion-aware loss, and for sampling time, we propose audio sync guidance. First, we go to motion-aware loss. Our goal is to generate motion that aligns perfectly with the audio signals. But if you see the image on the right, the blue pictures are calculation differences of the two consecutive frame latents. Movements are spatially and temporally localized. For example, striking bowling is spatially localized, and the dog barking and machine gun shootings are temporally localized. So in this observation, the model needs to focus more on motion. So we provide stronger motion-focused learning signals to encourage the model to better capture and align motion with audio cues. For each predicted frame slope set, we rewrite motion on the origin loss. The motion part is calculated by the differences of grounded frame latents to get the motion, and this motion is reweighted on the origin diffusion loss. And using this motion-aware loss, even though we use that motion-aware loss, the model is still hard to capture important but weak audio signals. So we skip the audio. We propose audio sync guidance, which skip the audio layers to make the model off-sync, and use the differences of full model and off-sync model to guide synchronized generation. So we apply this audio sync guidance, and they are the results of that our approach. The first column is applied audio sync guidance, and second one is only use the full model, and the third one is use of only the off-sync model. So our model is capture the weak signals such as the crisping sound. So leverage this crisping sounds to hitting the targeted object. But the second ones could not hitting the proper object, and the third one is just out of sync. But even though we skip the audio layers, we can see it can generate the same visual motion without synchronization. Synchronized has the same habit. And this is the result of the applied audio motion aware loss. The left one is they apply the motion aware loss, and the right one is without motion aware loss. We can see the lines rolling and frog crawling motion is properly initiate and terminate in synchronization. So we can see the result as can generate video, synchronized video, but existing sync metrics do not align with actual results. Sorry. So in this table, each existing metric score the I2V, which is a synchronized model, and Syncphony, which is synchronized model. But the existing synchronized model provide more score on unsynchronized one than the synchronized one, and which are not aligned with the human score too. So we propose a cycle sync, which is a synchronized metric based on the video to audio reconstruction process. This process is so simple. Using the audio condition, we can generate the synchronized video and use the video to audio model to recover the audio. And in these videos, we detect the peaks each audios and compare those temporal peaks to get the final score. So the cycle sync means to evaluate whether the motion in a video provide enough signal to reconstruct the temporal structure of the original audio. And this is the result of the cycle sync. And as you see above these tables, cycle sync achieved the highest positive correlation with human preference, but other prior metrics show weaker or negative trends. And this is the table I shown before. Cycle sync only align with the determinant of the human score. So this is our quantitative scores and our model. Then we're going to conclusion. So our work contribution is to build a high-quality audio-synchronized video generation framework. For training, we propose motion laws, which encourage the accurate timing by emphasizing high motion regions. And for sampling, we propose audio sync guidance, which enhance sensitivity to audio signals during inference. And then, to better evaluate synchronization accuracy, we propose cycle sync, which is a video to audio-based metric that measures whether the generated video retains sufficient motion cues to reconstruct the original audio. Yeah, so this is the end of my presentation, and now we are search on the fast-speed sampling and like that. We're archiving soon. So yeah. And my presentation is the end. And if you have any question, then feel free to ask.
Thank you for a great presentation. So actually, I have some thoughts about connecting our two papers. So in this paper you presented, there is a challenge about aligning the audio with the video. So actually, it is the same as the conditioning. And it is how to make the condition more effective, how to enforce the model to have this conditioning. So first, for this, I'm thinking that if I use some method similar to my approach, I will construct the video to some special videos. For example, instead of the actual videos, I will directly use the audio itself to construct a video that, for example, if the audio is in a high peak, then the frame will just be pure white, and if it's low, it will be black. And if it is in the middle, I will just have just convert it to 0 from 1. So that each frame will faithfully show like the energy of the sounds at each of the time step. So in this case, the model must read and connect each of the specific time steps to the audios. And then this will strongly encourage or strongly enforce the model to align this time. And then we can leave these parts and finally go back to the prediction model to the traditional training. But after a second thought, I'm thinking that actually this kind of losses is another kind of construction that can provide some guidances or some special gradient directions for the attention model still to the same direction that it must learn to align this uh, specific time step with the video and audio. So do you think the method used in my method will also work in this case?
If I clarify your question, actually, I couldn't catch up, but you mean that why don't we use that audio peak for loss condition? Is it right?
And so what I just said is that I am thinking about an alternative way to also to encourage or enforce this accurate time alignment. So I'm thinking that can we have the use some special video to train your model. That the video is not the actual video, but is a video with each of the frame constructed according to your audio. For example, if the audio is at a high peak, then the video shows white. If the audio is at a lower peak, and it will show black. So in this case, the model must learn to follow the audio to confront the color of the frame. Do you think this method will also be regarded as kind of laws that can, or a training pattern that can encourage this kind of accurate timing and alignments?
So you're talking about creating a synthetic pair between audio and video where
Yeah.
whenever there's a peak in the audio, in the video, there should be also a sudden change in the video. And the sudden change you kind of artificially introduce by yourself.
Yes. So and the frame is very simple. It is just a toy task, but constructed to directly enforce this accurate. Maybe let's just go back to some traditional question. This is just like so. Do you pre-train from some pre-trained? Do you use some pre-trained diffusion models, or you train your model from scratch?
Oh, I used the pre-trained model, and I didn't train from scratch all the layers from scratch. I just trained the whole audio layers and fine-tuning the later blocks for constant motion generation.
I see. It's like you repurpose a pre-trained model to add some additional layers and then do the fine-tuning. I see. This is actually really very reasonable strategy academia planning because we cannot train like a very complicated model from scratch. Can you please go to the pages about your motion aware loss?
Oh.
Like some questions accordingly. So here, how do you know that some frames or some specific motions will be correlated to the audio?
I understand your question. Um, mm, oh, we don't know those motion is related to audio, but this is not the purpose to directly align with audio. this helped to the model to catch more attention on the motion. So this model can, if the model concentrate on the motion and learn that what this motion is caused by. If the motion is caused by audio, then the model tried to relate it, motion and audio. But if the motion is not related audio, such as the camera zoom in or out, the model trying to learn that motion that unrelated to audio. So we just encourage the model to learn the motion and model to distinguish that the audio related motion or would not related motion. Oh, yeah. So it could be the
I see.
answer.
So it's more like a law that enforces the or having some emphasis on the motions instead of directly emphasis with correlation. And the model needs to first make the motion correct and then use the correct motion to like implicitly learn how to align with the audio. Is this the idea? Yeah, or the
Oh,
intuition?
yeah.
Yeah, this actually makes sense. So it's like more some indirect way that because once the audio is given, actually all the motions are already placed in some aligned time steps, so they must have been aligned with the prompt. Yeah, I see. This makes sense. So maybe could you please go to the slides about the guidances? You have some audio related guidances. So this is like some strategies to similar to the classifier for guidances.
Yeah.
So how do you actually? I'm thinking that it is more similar to some like perturb attention guidances. This is also a work that creates some guidances by skipping some layers. So here, how do you implement this skip? Do you just replace it with identity or you replace it with like 2V or something?
2V?
Yeah,
What
so for example, if you just replace it with identity, so you skip this once, it may already, in the floor model, it may already been converted into the new feature space by the 2Q, 2K, 2V, 12, like those. So maybe some skipping strategies to use 2V instead of directly the identity. So are you using this strategy or you just use the direct skipping or to replace it with identity?
Uh,
So the question was just how do you have these skips? How do you implement the skips?
skip. In this means
Skip.
I skip the whole audio layers, not just condition on the audio to zero. Is it right?
So you just assume that there is no that layer. So it's like replacing those layers into an identity model. Like example, input is X, so the output is also X. Is this the implementation here? Or it's more like a classifier free guidance that you have some empty audio as the input, which is your implementation here.
Yeah, I just skip the audio layers. It's not the replacing into the model.
It's equivalent to replace these to some empty layers. Is that correct? Maybe that's I think maybe you so I think you're what you are presenting here, it seems that you just literally skip, so it is somehow replacing it with the identity layer, that it will do nothing on it. So it will not considering the audios. Is that
Ah,
similar to your implementation? Or?
oh, you mean that audio layer has the identity of the related to the, for example, the dog's semantic identity?
No, it is just I was just asking.
Sorry, I'm so
Yeah,
sorry.
maybe let's skip this question. So so what about for example, so you in the same paper you also propose a different metric that will better align with
Yeah.
your vision and with the user's feedback. Yeah, I think actually this is very this also makes a lot of sense because it's kind of related to the for example the perceptual loss that you use another pre-trained model to have this prediction. But I wonder, because this kind of video to action, video to audio for prediction may also based on some assumptions. For example, there is no noisy background. So how is the metrics for the ground truth videos? Will it be just perfectly high, or it will also have some gaps?
Mm. Oh, yes. As you like your concerns, the pre-trained read to a model have some
Yeah,
um yeah have some such background sound or bias because they just generated model.
yeah.
Yes.
Because the models didn't know some background. For example, some videos may have background noises, but
Yeah.
this retrained V2A doesn't know this background noises. So it will not generate this. I think only considering the peaks as shown here is already very will make the model very robust in this case because those background noise will just be some like low frequency ones and will not show as peaks.
Yeah, so we can control the how much we can reflect that pix noise. So we can control this is the hyperparameter to reflect how much the um audio or as sound to reflect. Yes.
Yeah.
So yeah.
I see. So it's like you are making a pooling or some high pass filters to the peaks so that you only consider the most important ones.
Yeah, so I use this that hyperparameter um, that is utilized by the existing metrics, such as the the existing metric that I shown as avial line. So which is the detected peak of audio and visual. So we use that parameter to track the audio to audio peaks. Oh.
I see. Thank you. And sorry that some of my questions may be too related to some technical details, so I did not very easy to answer. But anyway, thank you very much for your answering and for your great presentation. Do you have more questions or?
By the way, a quick comment. So you can also use Slack for further communication. Maybe it works better there.
Yeah, sure. Thank you.
Thanks so much. Maybe I have one more quick question about the work. So, why do you think do you agree that when you train a video to audio, or sorry, audio to video model from scratch from some paired data of audios and videos, do they typically suffer from the misalignment issue?
Um, Actually, I trained from scratch.
It doesn't have to be from scratch. Sorry, I made a so it's not an important word, right? So when you just train, let's say fine tune your model on audio to video, do you think the model will not pay too much attention to alignment in
Yeah,
general?
yeah. So I just tried the conquered all the features and
Mm,
did the self attention, the whole self attention. So it was very hard um, to attention another modality such as the s- working like cross attention, but it uh, but it doesn't work what we expected. So
mm,
we just changed the architecture to just cross attention for
mhm,
um, yeah, so cross attention. So yeah, I'm so curious that how so how to train more focus on the audio different modality on the self attention rather than the same modality.
mhm. Okay, it's good to know that it's something inherent in the model and the data. And maybe humans are kind of particularly more sensitive to the alignment issue. I
Yeah,
think
and
the
also,
same is true for like, sorry, please go ahead.
I'm just giving a quick comment that Jibin just mentions that how to use modalities, different modalities in self-attention. And I'm thinking that some of the text-based attention model is also using self-attention. So I think maybe it is just harder to train the cross-attention because you have to align different modalities in the same feature space. But maybe with some data, it will be able to achieve. But this, I think it is more like a trade-off because if you add more layers, the model will be slower. And if you use fewer layers, it will be quicker, but it will be harder to train. So I
Mhm.
think maybe with some training strategies and maybe with longer trainings, it will work. It's going to be.
Mm. So you're saying maybe also be the model capacity and
Yeah,
training
also
versus.
because the text and image generation can do together. You can use text and like videos or images, use
Yeah.
self-attention to concatenate them, and this will also work. So if text can work, then there's no issue at the audio as well. But not
Mm.
because text even has no temporal dimension, but audio still have.
Mhm, mhm.
Yeah,
Yeah, yeah,
please.
that makes sense to me.
Yes, yeah, so I wanted to add more layers um, 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 or diminish the layers, but it was very hard to train that every model architecture. So
Mm.
Yeah. So if this just works, then we can just keep the same one because this is actually lots of engineering. The engineering is something we will not say or present in paper presentations, but it is also really important to actually train a model towards the fully functional. So yeah, it's still good that you can make your current model work in the current architecture design. You don't need to make it self-efficient.
thank you for your insightful answer.